Other questions? Okay, so we said that this is an example of an AC current or alternating current. It constantly changes its sign. Once positive, it's running in one direction. At the next instant, it's running in the opposite direction. Now we can, this is the most general kind of current that we use, the AC current. The electric current of the city current, the electricity is an AC current with a frequency 50 hertz. It changes its sign 50 times a second, or let's say 100 times a second. Now, one of the reasons, there are various reasons why we are using an AC current rather than a DC current. One is easier to generate. Let's just imagine, if you remember, we were discussing the electric motors. We had such a loop. In a magnetic field. Now we said that if you send the current in this loop, then this will act like a magnetic dipole, and the magnetic dipole will feel a torque if it is not aligned with the magnetic field. So it will rotate it. Now, but what happens if we take the same motor, the electric motor, and by some means rotate the circuit ourselves by some force? It can be a water falling water mill. It will be rotating the mill, and so it will be rotating this motor, or a steam generated by some coal, burning coal, or some nuclear energy. So you can just find other means of energies, or some winds rotating the wind turbines, and which are connected to this circuit, this wire, which cause it to move in a magnetic field. If the magnetic field is uniform, the flux going through this loop is, I will not be paying attention to the signs, but it will be just the magnetic field times the area. This is the flux that is going through this loop. So you can just say, okay, this is equal to B times A times cosine theta. And if you just cause this object to rotate by a constant frequency, let's say theta is a function of time, is equal to omega t plus some delta. It rotates with a constant frequency, and at t equal to 0, it might have some initial angle. Then the flux will be changing as a function of time. This will be BA cosine omega t plus delta. Now we know the Faraday's law. It says that the EMF induced by this changing flux should be minus d phi b by dt. This will be B times A times sine omega t plus delta. So this is just take a wire, rotate it in a magnetic field, and then you have this AC EMF source. It will be constantly changing in time, and this omega is the omega of the how fast it rotates. So you can easily create the create an AC generator. In a sense, yes. Basically, since you are changing the direction, you see a changing EMF source is basically creating an electric field in the wire which constantly changes its direction.
Do you see that some electric motors have brushes on them, and then there are brushless motors which run with DC?
Now, brushless motors usually run with AC.
And then I was going to ask how brushless AC motors run.
I mean, they should be running on AC. Brushless motors should run on AC. Because what happens in an electric motor is This is your dipole. You send some current. And let's say you are sending current through this end, and that comes from this end. So if the current is running in this direction, what is the direction of the magnetic dipole moment? This way. Something like this. Let's say the magnetic field is in this direction. So if this is the magnetic dipole moment, it will feel a torque in this direction. Now, when it is aligned with the magnetic field, there won't be any torque. But if this is a massive object, it will have an inertia, so it will keep rotating. Then the dipole will be, again now, the dipole will feel a torque rotating, trying to align it in the direction of the magnetic field. So if you don't change the direction of the current, this will be how its motion. It will not be rotating. It will be just oscillating. So what you should do if you want to keep this rotating is, let's say you started here. When you reach at this point, you should change the direction of the current, so that the magnetic dipole will be pointing in this direction, and hence it will, as it's trying to align with the magnetic field, it will keep rotating. Now, how can you change the direction of the current? Either use brushes in a DC motor, in a direct current motor, or use an AC current. So the frequency, of course, in that case, you should match the frequency with the rotation frequency of your motor.
If you think about vacuums, and most of them, like new ones, they have a switch on them that you set up the RPM of the motor, and then how does that work? Because city electric, it's on 50, 60 hertz.
Well, I don't really know the details. I would rather use brushes in that case. And to change the RPM, just change the resistance so that the torque will change, the angular velocity will change. I don't know how they actually do it, but that would be my guess. Take the AC, convert it somehow to DC, then use an electric motor with brushes. In that case, you don't have to worry about changing the direction of your current. So the only thing you have to worry about is adjust the torque. And you can adjust the torque by lowering the current. So that would probably is just a variable resistor.
EMF shouldn't be there an extra omega.
True. Other questions? Yes.
Why did we give the theta function?
No, because this is the angle between the magnetic field and the area. And in this problem, we said that let's just, some effect is rotating this wire loop. And so if it is rotating, then the angle will change in time. If it's rotating with constant angular velocity, it's omega t, and this is the orientation at the t is equal to 0. So this is the most general form. What is omega? Well, it depends on your device. Now let's see some simple circuits with AC alternating current EMF sources. Well, this is what we will use to show an alternating AC source, AC EMF source. And let's say this is epsilon 0 cosine omega t. This is how it changes as a function of time. And let's say that this is, we connect it to a simple resistor. Well, in this case, still we can use the Kirchhoff's rules. Let's choose a positive direction of the current. This is I0. across the resistor, the potential drop. Now this is not I0, I times R. Then we have the potential drop across this alternating circuit. Well, since it's constantly changing its sign anyway, the sign of that term is not really that important, so let's just add it with a plus sign. This should be equal to 0. So this just tells me that I is equal to epsilon 0 over R times cosine omega t. Well, in fact, there's nothing interesting over here. It's just that epsilon divided by the resistance, that is the current running through the circuit. Its maximum value is epsilon 0 over R, the maximum value of epsilon divided by R. Well, nothing much interesting.
There's a minus sign.
So basically, we don't know where is positive terminal and negative terminal of such a.
It's constantly changing. I mean, it's just convention. At t equal to 0, you can define the positive and negative, so then you are done.
So we can choose whichever direction is correct.
Yeah. The only thing is that you have to be consistent if you have more than one circuit, one loop that you consider. Again, we have this AC source, but this time let's say we have a capacitor. Let's say this is positive, this is negative. What is the potential drop?
What's the direction?
Well, it's Q over C plus epsilon 0 cosine omega t. This is equal to 0. So Q is equal to epsilon 0 times C times cosine omega t. Well, you see, I is nothing but dq by dt. In this problem, I is positive if the charge is increasing. So that means this is equal to epsilon 0 C times omega times sine omega t.
Isn't there again a minus sign?
Now this time I max, the maximum current is epsilon 0 over 1 over omega c, which is usually written as x0 over xc. Xc is the capacitive impedance. Well, it is similar. What Xc is, it is similar to the resistance in a sense, in the sense that the maximum current is the maximum EMF divided by this impedance. But it's not really a resistance. You see, epsilon goes with cosine omega t, whereas the current goes with sine omega t. When the EMF is maximum, the current is a minimum. When the EMF is a minimum, the current is a maximum. So the maximum of the current and the maximum of the EMF, they don't happen at the same time. Now let's try to write this sine omega t as cosine minus epsilon 0 over 1 over omega c cosine omega t minus pi over 2. You agree? Well, you see, this is our equation we said. Once you write this equation, you have to be consistent. The solution of this one is minus epsilon 0c. That is why I insert the minuses over there. In this first equation, I said that the sign is, well, you can just choose whatever you want. It's constantly changing anyway. True. But you see, this is consistent with this equation only if I have a minus sign. Well, if I had given it a second thought, I would have started with a minus over here so that I won't have any minuses over here. But once I put that plus sign over there, I have the minus sign. Both are true. It's just your convention. How do you choose your convention of that alt AC source? This one? True, that's plus. This is plus. I have this plus now. Well, it's not so easy. One thing is changing alternating currents will be changing your circuit significantly. Depends. Yes and no. In the sense that we will see later on in more complicated circuits. For example, in a realistic circuit, you will have some resistances over here. In this case, Q is, let's see, Q is fixed by this equation. If you have epsilon 0c, that's fixed. But if you put a resistance, things also start to change a bit. In the sense that if there is a resistance, the current cannot increase really fast. So if the circuit is changing very fast, if the omega is very large, we will study such circuits that there won't be any charge buildup on the capacitor. Because the capacitor will never have enough time to charge to a significant value if there's a resistance. Well, it will contain a very small amount of charge, and it will be constantly changing its orientation, but that will be insignificant if omega is very large. Yes. It will just behave like a short circuit if omega is very large. Whereas if omega is very small, that in that case EMF will be almost a constant, then it will behave like an open circuit. Well, there is a single element circuit element left, the inductor. Let's put the inductor. So let's say we are going from,
Isn't the alternating current source the inductor itself?
now there is an alternating current source. And then there is the inductor.
But isn't it in itself an inductor? Or within it?
This AC source.
Yeah.
Not necessarily, it can be just your city electricity. You just take an inductor and connect it to this plug over here. And well, of course, if this is just a short, you will just blow up the fuses. But what if it's an inductor? You see, the fuses will blow up if the maximum current goes above a limiting value. You see, if the capacitance is small enough, then it will not blow up because the maximum current will be small. Let's see what will happen in this case about the maximum value. From B to C, the potential drop is positive or negative, LdI by dt. It doesn't matter. Well, let's see. Let's look at, with time, the I by dt will be changing its sign anyway. So let's look at the time when the I by dt is positive. If the I by dt is positive, then the inductor will be pushing it in the other way around. So there will be a potential increase, not a drop, so it should be negative. At a given time, I assume that the I by dt is positive. There will be such times. So I can just look at those times the I by dt is positive. If the I by dt is positive, then the current is increasing in this direction, but the inductor will try to resist that increase, so it will try to push it in the other way. So it will behave like a battery whose positive terminal is over here, negative terminal is over there. So it's positive. Positive or negative? Let's write it down. Assume the I by dt is positive. Then the inductor will push the current in the other way. That is, this is the positive, this will be the negative terminal if we use the analogy with the battery. That means there is a potential drop as we go from this point to this point. A potential drop is LdI by dt, a positive drop. LdI by dt is a positive number, so it's positive. And then plus the EMF source. So the I by dt will be equal to minus epsilon 0 cosine omega t over L. Or if you just integrate it over time, I will be epsilon 0 over omega L sine omega t. I max is equal to epsilon 0 over omega L, which we define as epsilon 0 over xl, and xl, this is just omega L, this is what we call the inductive impedance. Now these impedances, they just behave like resistances only in the sense that they determine what the maximum value of the current is. But it's not really, you see, I is not equal to epsilon over xl. Because if you look at the current, it behaves like the sine omega t, whereas epsilon behaves like the cosine omega t. The current is not equal to the EMF divided by the impedance. But the maximum values are. related in that way. So this is something you have to pay attention to. Now let's see. We have these three circuits. This is for the resistor. This is for the capacitor. This is equal to minus epsilon 0 over XL times cosine omega t minus pi over 2. This is for the inductor. Now, okay, they will look similar. Well, let me also change that to XC. XR is just the resistance. XC is 1 over omega C. XL is omega L. So at the maximum, they just look similar if you identify the corresponding impedance, resistive, capacitive, or the inductive impedance. The phases are different. You see, first, the current across the capacitor. Or let's write the potential differences across the capacitor. No, the current. First, the maximum for the capacitor arrives. So at t is equal to minus pi over 2 omega, I will be maximum. So the capacitive current leads the resistive current in a sense. First, this arrives. If you have many circuits, or if you just connect all of these in parallel, first the current in this wire will be maximum, then across the resistor, and then the inductor. Because of these phase shifts, because of these numbers over here, 0, pi over 2, and minus pi over 2. They will not be at a maximum at the same time. First, this will be at a maximum, then this will be at a maximum, and this will be the latest one. Now, these 0, pi over 2, and minus pi over 2 will be important also later on. Just keep those things in mind. For the capacitor, we have a plus pi over 2. For the inductor, we have a minus pi over 2. And for the resistor, we don't have anything. Now, what kind of a circuit would you like to study with an AC source? Well, let's start with RC. Okay, we don't have much time left, but let's just do a couple of steps and we will continue tomorrow. So we have a capacitor and a resistor. Epsilon 0 cosine omega t, C, and R. Potential difference across the capacitor, I plus minus Q. As we go from this point to this point, the potential drop is Q over C. as we go from this point to this point, the potential drop is I over R. This is equal to epsilon 0 cosine omega t. Now I change my convention. Before I would write this on this side with a plus sign. Now I'm writing it on that side with a minus sign. It doesn't make any difference.
It makes no difference.
No. I'm just changing what I call t is equal to 0. That's the only difference. And I is equal to dq by dt. So if you just put it over here, we have dq by dt plus q over rc. This is equal to epsilon 0 over r cosine omega t. I also divide it everywhere by r. Now, since we are pushing this circuit with a frequency omega, the current will also oscillate with the same omega, or the charge will oscillate with the same omega. Let's say Q is equal to some number, A, times cosine omega t, plus delta. Let's look for a solution of this form. Delta might be different. Delta need not be, this is 0. There we can have a delta. If you note over here, we had various deltas if we just had one of them. 0, pi over 2, or minus pi over 2. Now that delta can be something else, we don't know. We need to figure out what A should be, what delta should be, so that this is a solution of that equation. Let's just substitute our function over there. So we have minus A omega sine omega t plus delta plus A cosine omega t plus delta over RC. This should be equal to epsilon 0 over R cosine omega t. This should be satisfied at all times. Well, there are two things you can do. You can say, okay, sine omega t plus delta is equal to sine omega t cosine delta plus cosine omega t sine delta, and do the same for the cosine. But I will rather go for an alternative. If this is true for all times, then it should be true at time t is equal to 0. Well, at time t is equal to 0, the equation gives me minus A omega sine delta plus A cosine delta over RC. This should be equal to epsilon 0 over R cosine omega t. And it should be also true when omega t is equal to pi over 2. Well, this is at t is equal to 0. This is at omega t is equal to pi over 2. Well, when omega t is equal to pi over 2, sine of pi over 2 plus delta is cosine delta. Cosine delta. Cosine of pi over 2 plus delta is minus sine delta. This is equal to 0, because cosine of pi over 2 is just 0. So we need to determine A sine delta and also A cosine delta, and we have two equations to solve. Oh, sorry, the first one is 1. There's no cosine, because omega t is equal to 0, cosine of 0 is 1. So we have two equations to solve for the two unknowns. And, well, we will continue tomorrow. Now, one thing that will be interesting will be what this I is. A is. A will be epsilon 0 divided by square root of xr squared plus xc squared. You see, we said that xr and xc, they are just like resistances when we are talking about the maximum values. But although here we have connected them in series, we are not adding the impedances. We are adding their squares. and taking the square root. And this is, in general, defined as epsilon 0 over z. So this is the impedance of the circuit. And in this case, the impedance is given by the sum of the squares of the impedances. Now, we will study this in more detail tomorrow. Any last minute questions? Yes, because cosine pi over 2 is 0. You see, cosine pi over 2 is 0. See you tomorrow.